For subtopic 10.2 fields at work, when we're talking about charges, we were looking at fairly small scenarios, so charges between plates or small charges in the fields around them. In this scenario, when we're looking at gravitational fields, we need to look at much larger scales. So you can see here the title of Leaving Earth. We're basically looking at planetary scales for looking at how we can put gravitational fields to work, or the work that we need to do in dealing with gravitational fields. So to start off with, we're going to very quickly just refer back to Unit 6 on circular motion and gravitation. In Unit 6, we identified that we can figure out what the speed of an orbit should be for whatever the height of, or the radius of that orbit is around a mass. So identified that for orbital motion, the speed of orbit is given by this equation that we'll have a look at. And that equation is that the speed v is equal to root gm on r. Now if you want to revise that one, go back and have a look at the Unit 6 videos. In Unit 6 I didn't highlight that equation, but I need to highlight it now because it is part of Unit 10. So we can see there the gravitational, when we're dealing with gravitational fields, the speed of orbit can be figured out by considering the root gm on r. Now for Earth, we know that that mass m is constant, as is the value for g. So we then have a relationship then that v is proportional to 1 on root r. So that basically means that the higher the orbit, the slower the orbital speed will be. So just a quick point to note there, linking into Unit 6. Now that means that if we want to launch an object into orbit, let's say a satellite, that means that we need to do two things. First of all, it needs to gain gravitational potential energy. So if it's on the surface of the Earth, it's going to have a certain gravitational potential, and so it needs to be raised to a higher gravitational potential. That means it's going to gain gravitational potential energy. And it also needs to be sped up so that it reaches that orbital speed, and so it also has to gain kinetic energy. And obviously that the amount of kinetic energy that's going to gain will depend on the orbital radius that we're looking at. So we're going to have a look very quickly now at some different orbits. So while orbits of any height are theoretically possible, there are obviously a few conditions on what's practically possible. For example, we can't really have an orbit that's only, say, 100 meters above Earth's surface, given that air resistance would significantly impact on that, and not to mention buildings and mountains and whatever else. So we're talking in theory about what we're looking at here. While that's theoretically possible, there are two that we're particularly interested in. And those particular orbits are, have the reason why we are interested in them is because of what they're capable of, or what the benefits are for these two orbits. So the first one that we're interested in is known as a polar orbit. Now that name is slightly misleading. It's not always going to be that it passes over both the North and South Pole, but that's generally speaking the way that you'd see these orbits happen for satellites around Earth's surface. So they're usually going to pass over the poles, which is why we get the name polar orbit. Now these orbits are about 800 kilometers above Earth, so that's not the radius, that's the height above Earth's surface. And the reason why they're useful is that they allow all parts of the Earth's surface to be seen in a 24-hour period. So that means that you can scan across the whole Earth using a polar orbit in a 24-hour period, so once per day. So that means if you want to look at trends across the course of a year or a number of years, you can scan the Earth once a day and go through and analyse that data, and you'll get a good trend over the course of a year. The second type of orbit then is a geosynchronous orbit. If you think about the breakdown of that word, geo meaning Earth and synchronous meaning that it's in time with. So a geosynchronous orbit, first of all, the height of that orbit's about 36,000 kilometres, so a fair bit higher than a polar orbit. And because it is much higher, it's going to be moving much more slowly, and that means that it's not going to orbit the Earth anywhere near as quickly. So for a geosynchronous orbit, or a geosynchronous orbit orbits the Earth. Let's put it a better way than orbits the Earth. Has a period of orbit of 24 hours. So whereas for a polar orbit, all parts of the Earth can be observed in 24 hours, that means it's going to be orbiting the Earth multiple times in one day. For a geosynchronous orbit, it has the same same period of orbit as a day. So once every 24 hours, it's going to orbit the Earth. There is a sub set, I suppose, of geosynchronous orbits known as geostationary orbits. So these are specific types of geosynchronous orbits. For a geostationary orbit, it still has that period of 24 hours, so it is actually a geosynchronous orbit. But there's one aspect of a geostationary orbit that makes it even more useful. And as the name suggests, you can sort of get it from the idea that it's stationary. So what it means is that for a geostationary orbit, it's a geosynchronous orbit above Earth's equator. And what that means is that if you were to imagine observing the orbit of a geostationary orbit, it means that the satellite will always be in the same part of the sky. So when viewed from Earth, or from the surface of the Earth, the satellite will always be in the same part of the sky, or at the same position in the sky. So if you think about satellite dishes that you might see, so even things like satellite dishes for pay TV, you'll notice that they're always pointing in the same direction. That's because there'll be a geostationary satellite that's up in the sky that you know that it's always going to be in that same fixed position because it's rotating around the Earth, or orbiting the Earth at the same time as the Earth is spinning. So it makes it good for those sorts of orbits are good for communications. So orbits are one way that we can make use of gravity, and so be able to do something meaningful and putting satellites up in the sky. But if we want to look further afield, we actually need to escape Earth's gravitational field. And there's a couple of things we need to consider there. So to escape Earth's gravitational field, so we're no longer just sort of in orbit around the Earth, we're going to be looking at what happens to, say, get a satellite or a probe, out to the far reaches of our solar system. We're going to need to do work on whatever that object is. So work must be done on the object, let's call it a probe in this case, needs to be done on the probe to move it to infinity. So the reason why we're talking about infinity here, that's the reference point that we use for gravitational potential energy, and what that means then is to move an object to infinity, we need to overcome both, it needs to have kinetic energy, so it means it's kinetic energy as it's being launched, so kinetic energy at launch must overcome its gravitational potential energy. Or not necessarily overcome, it's a better word to use there. Actually no, overcome is quite an appropriate word there, considering its gravitational potential energy would be negative, so work would need to be done. So what that means then, let me just draw a diagram to help explain this scenario, because it might not be immediately obvious just from those words. So imagine that we have Earth positioned here, and we have some probe or something or other that's going to be launched out into space. We need to get it to escape Earth's gravitational pull, so that means that its gravitational potential energy needs to be 0 joules per kilogram, sorry, 0 joules. Not talking about potential, we're talking about the energy. That means that over here it has a certain amount of gravitational potential energy that would be given by negative g m on the radius of the Earth. So given that so capital M would be the mass of Earth, lowercase m is the mass of the object itself. Notice the negative there because we're closer to the Earth than we are to 0, so if this is our 0 point, we'd actually need to do work to get it away from Earth, and so that means that the gravitational potential energy there will be negative. In order to get that rocket or that probe all the way out to 0 energy, 0 gravitational potential energy, it's going to need to have a certain amount of kinetic energy. We're going to call that V escape. So that's how much kinetic energy it needs in order for it to blast off and reach this point over here. As we said, the kinetic energy there is going to have to overcome this gravitational potential energy, and we can see then that if we add those two together, EK plus EG for the probe eventually is going to have to be equal to 0. So that means the kinetic energy that it needs at launch has to be equal to the negative of the gravitational potential energy. So we can substitute in the two equations there. Half m v escape squared is equal to, now notice that the negative here is going to cancel because it's negative Eg, and so we'd have mass of the Earth, mass of the probe, and radius of the Earth. Notice there that the masses of the probe itself cancel, so we end up with the escape velocity. So to get away from Earth, we can calculate what the escape velocity is, multiply the value of 2 across the other side, we end up with 2gme on re. So to figure out how far something needs to move in order to be able to escape Earth's gravitational pull and move out into deep space, that's the value that we'd need. Point to note here too though, in this scenario we're really talking about an unpowered probe. So that value, or that equation, corresponds to an unpowered probe or object. What I mean by unpowered is that it doesn't have any continued thrust being acted on it. If you think about rockets, they typically will increase their speed. So they're initially stationary and they'll get faster and faster and faster as they launch. So they increase their speed throughout launch. And so we can't really consider the velocity there to be quite the same. because they have the ability to change their speed as they continue to get higher. But having considered that, it is that we still have this idea that we can figure out what sort of speed is needed to get away from Earth, and so it's more efficient to get up to that speed as soon as possible. So reaching the escape speed, you could in theory just have a rocket that is very low thrust, and if that thrust was applied for long enough, it will accelerate to a speed where it can escape Earth's gravitational pull. But if you can do it more quickly, if you can get that rocket moving faster more quickly, then it's going to be a much more efficient process. We'll have a look at a couple of those sort of scenarios in class where we can figure out whether or not things will make it away from Earth's gravitational pull, and even look at some of the orbits that might result of something that's not travelling fast enough to escape Earth's gravitational pull. But otherwise, that concludes Unit 10 on fields.